So hopefully you're starting to see a pattern in these problems where if it's going to end up being a du over u pattern, so if we're going to be able to integrate it to a natural log, typically the numerator is going to be some form of the derivative of the denominator. So if we have a rational expression, we have to see this pattern where the numerator is 1 degree less than the denominator was. And if you look at number 8, you'll see that that's not the case. Okay, so here we have x minus 1 over x plus 1. You'll see that the power of x is the same in the numerator and denominator. And so this is not going to fit into the du over u pattern as it's written here. What we're going to do, though, is we're going to turn that into a problem that looks like this. And so what I've done here is I have now a simple first term that is very easy for me to do the antiderivative of. And then I have the second term, or it might be the third term or the fourth term, but the last term will be in this form where the numerator is the derivative or some form of the derivative of the denominator. All right. So the way that we're going to take this problem from here to here is one of the few hard and fast rules that we're really going to have when we're doing integrations, and that is anytime you have a rational expression where the exponent is either the same or higher in the numerator, your first step is always going to be long division. Okay, so we are going to use long division, and once we do that, you're going to see how we turn this x minus 1 over x plus 1 into this expression here. So I'm going to come over here, we're going to go through this long division again, this polynomial long division. So I have x minus 1 divided by x plus 1. The original numerator is in here, and I'm going to make sure that I have a column for each power of x. Here I just have x to the first and then x to the 0. So I'm good there. I don't need to have any spaces opened up or anything like that. Here I have power of x to the first and then the constant. And then I have the thing that I'm dividing by, the original denominator. Okay, so as in all polynomial long division, I'm going to divide the leading coefficients. So x divided by x is 1. And then I'm going to multiply that 1 by the entire original denominator. So 1 times x is x. 1 times 1 is 1. And now I'm going to subtract x plus 1 from x minus 1. So x minus x is 0. Negative 1 minus 1 is negative 2. This is our remainder. So you can see how I used this information to rewrite this problem. When I divided x plus 1 into x minus 1, I got a 1 with a remainder of negative 2. So I have the 1 here. The remainder of negative 2 goes over the original denominator, and so I have a new form for this problem. So let's see what I'm going to do from there. This problem right here is very simple antiderivative. The antiderivative of 1 is x, and I'm going to evaluate that from 0 to 1. So that's kind of taken care of now, right? That's a known quantity. That's an easy one. I don't really have to spend a whole lot of time thinking about that. I'm pretty much good there. So I can take care of that way. What I really can focus on now is the second part where I have the negative 2 over x plus 1. All right, and you can see here what I did was I took the negative 2, I made it the coefficient of this integral, and now I just have a real simple 1 over x plus 1 integrand that I can focus my efforts on. So as I proceed here, I'm going to let u equal x plus 1, that denominator, very similar to the problems that we've done before, and then du equals 1 dx. So using this u substitution, I can rewrite 1 over x plus 1 as 1 over u du. Now I've gone from x's to u's, so I need to change my lower and upper limits. So this lower limit used to be a 0. I plug it in here to the x, I get 0 plus 1 is 1. Now my new lower limit in terms of u is 1. The upper limit was 1, in terms of x. I plug that in here. I get 1 plus 1 is 2. That's my new upper limit in terms of u. And here also I've taken this this first part, and I said x equals 1 minus x equals 0, so 1 minus 0 is 1. And now all I have to do is this integration. We know this pattern. 1 over u du gives us an ln of u. So now I have the 1 minus 2 times ln of u evaluated from 1 to 2. So I'm going to do the ln of 2 minus ln of 1. So I have 1 minus 2 ln of 2 minus 2 ln of 1. I know that the ln of 1 is equal to 0, so this entire term goes away. So I have 1 minus 2 ln of 2, and I could leave it like that. It's a little bit simpler if I bring this 2 as a coefficient up here to become a 2 as an exponent. So I'd have ln of 2 squared, and there I get my 1 minus natural log of 4. I don't know what the decimal equivalent or the actual value of ln of 4 is without using a calculator, and that's okay. Just like if I had an answer in terms of pi or in terms of e, I'm just going to leave it as natural log of 4. All right. So again, to kind of summarize, anytime we have a rational expression as our integrand and the power of x is higher or the same in the numerator as it is in the denominator, we're going to do long division, and then we're going to simplify the problem into a very simple part, and then a part we can use kind of a straightforward u substitution and get a 1 over u du. All right, the next problem we have is 2x cubed plus x, all of that over x squared plus 1. And you can see that we have that same pattern we talked about before. I have a rational expression. I have a quotient of 2 polynomials. The power of x is higher in this case in the numerator as it is in the denominator, or higher than it is in the denominator. So my first step is going to be long division. So I would encourage you to pause the video here and see if you can do. This is the setup. You see that I've left an open space for the x squared term. You could also write 0x squared in here if you wanted to as a placeholder. But pause the video there, see if you can do that long division. See if you can figure out how we came to this here, this 2x minus x over x squared plus 1. So take a second and do that, and then play the rest and see how you did. Okay, so as we do this division, I have the original numerator inside here. I have a column for each power of x. So I have my x cubed column, I have my x squared column, I have my x column. And then I have the original denominator that I'm going to divide by. So I'm going to divide the leading terms. 2x cubed divided by x squared. 2x cubed divided by x squared is 2x. Then I multiply the 2x by the x squared plus 1. So 2x times x squared is 2x cubed. 2x times 1 is 2x. And now I'm going to subtract. So you can see here that I just, I don't want to say by chance, but really just by coincidence I didn't get any x squared term here, and that's fine. I have 2x cubed minus 2x cubed is 0, no x squared terms, and then x minus 2x is negative x. And now you'll see that the power of x here is lower than the power of x here. That's how I know that this is my remainder. The negative x is my remainder. So I have 2x and then minus x over x squared plus 1. I could have also written this as plus a negative x over x squared plus 1. That would have been just as good. All right, so again, we've taken this rational expression with a power higher in the numerator, and we've divided it so that we get a simple antiderivative part here, and then a u substitution problem that eventually is going to give us a du over u kind of result here. All right, so let's see here. Okay, so we have the antiderivative of 2x is x squared. So I've done that part there. All right, so that's an easy antiderivative. Now I can just focus on this antiderivative right here. So I have the negative sign on the outside, and I just have x over x squared plus 1. I let u equal the denominator, x squared plus 1. Du is 2x dx. I really have an x dx here that I want to replace, so I'm going to divide both sides by 2. And I get du over 2 equals x dx. So this x dx here is going to be replaced by a 1/2 du. So I have a 1/2 du replacing the x dx. I have a 1 over u that is replacing that 1 over x squared plus 1. And now I have my good old 1 over u du, or du over u. That is going to be the ln of u, the natural log of u. So I still have my x squared here. Now I have minus 1/2 natural log of u plus c. All right. And then I have x squared minus, I bring my x squared plus 1 back here. So rather than the absolute value of u, I have the absolute value of x squared plus 1. All right. Now I could rewrite this a little bit. This coefficient of 1/2 could become the exponent there. Right. And now we think a little bit about, do we have to keep this absolute value symbol around this x squared plus 1? I would encourage you to leave it if in doubt. So if you're not sure if it needs to be there, leave it there. But in this case, you can see that x squared is always going to be a positive value. And if I add 1, that's always going to be a positive value. So the absolute value doesn't really need to be there. So I really don't need this absolute value symbol here anymore, because this quantity in here is always going to be positive no matter which x value I plug in there. So I could also rewrite this as something like this. Of course, a power of 1/2 is also just another way of saying the square root. So you could see it like this. Any of these would work. I'm really showing you these primarily just so that as you check your answers in the book or online, you won't be too surprised to see other kinds of forms of those answers there. All right. So again, to wrap up one more time, we always want to use long division on any kind of integrand that is a rational expression where the power of x is is either the same or higher in the numerator as it is in the denominator. All right. That's as soon as we see that pattern, we want to go right to a long division and reduce it to this type of a problem and then move on from there.